Now let's talk about the homework on page 230. First, problem 1. We're supposed to integrate this thing independent of path. To do that, we first have to prove that the Green's theorem applies, right? So then, okay, these are the all. This contains all four first problems. So then we prove that P2 equals to Q1, and once that's done, we make up some antiderivative by some kind of an inspection, okay? And for now, just like example A on the previous page. So we come up with the antiderivative, and then we evaluate it at two ends, and that gives us the right answer. Problem 2 is I think the same story actually. That we have we first show that P2 equals to Q1, right? Yeah, and so apply the Green's theorem and dig out figure out what the antiderivative is by inspection, pretty much, and then evaluate it at both ends. And then problem 3 is slightly different. Now we're not just integrating through any path. We're integrating a gamma in the only along the unit circle, which is fine. That just means that we're going to plug everything in like we used to do. And x is cosine theta, y equals sine theta, and we'll integrate from 0 to 2 pi, and you plug it in, and some kind of answer comes out to be easy. This happened to be 0, which checks out to be correct. And then next, problem 4, we have this integral. The question is, what kind of restrictions do we need to impose on this thing? The restriction mostly has to do with the denominator should probably not be 0, okay? So other than that, which in this case means the paths cannot cross the x and y axis, as I say on this side. So then otherwise we just I cranked out the antiderivative, okay, by sort of a trial and error. But in reality, you can just do partial integration the same way you might do partial differentiation, because and which we'll figure that out real soon, okay, as you move on to the homework, and you can no longer do stuff by inspection. Then you ask yourself a basic question: is why don't I just integrate this thing? So anyway, doing partial integration as an opposite of differentiation, and then you're going to come out with something like this, which happens to be that, okay, that's the big F, and then evaluate it at the two ends, which gives you some kind of an answer, which is right here. So next, let's look at problem 5. Let's see, what is it? Gamma is a regular closed curve that's in the first quadrant, okay? So x is bigger than 0, y is bigger than 0. We are supposed to integrate some gamma, of this big long thing, okay? And let's see. Give me a second here. What do I have? So anyway, this we simply, well, first this function is the denominator doesn't go to 0 in the first quadrant, okay? If x is bigger than 0, y is bigger than 0, then the denominator will always be positive. Thus, just because of the 4y squared, okay? Never mind the other stuff. Y is bigger than 0, then everything is positive, so the denominator is positive. So everything looks good. And then the next thing we will confirm is the Green's theorem rule, where that is, we need to confirm that P2 equals to Q1, which I did. I assume it doesn't. I don't say that here, but I'm sure I did it. Okay. The partial differentiation using a calculator is much easier to do than some kind of integration, which doesn't always work out. So anyway, I did the partial differentiation and confirmed that P2 does equal to Q1. So then the integral is 0 because we're going clear around, right, by the Green's theorem. which is fine. But then when I looked at the answer of the book also gave us the antiderivative. What is the big F for this thing? Which I thought, okay, so by now, the way we calculate big F, instead of by inspection, like the book one says in example A on the previous page, it's better that we just do partial integration of one of them, either P or Q, okay? And that will give us the answer, which is what I did. So here is what I have. As you can see, the partial integration, we have, that is the, let me see. Okay, this part equals to P2, and the partial integration is equal to this pile of stuff, okay? And then partial integration of that's Q. The thing in here is Q. Partial integration, that would be Q1, which does check out. I guess that's where I check things out. That I said that I make sure that P2 does equal to Q1, as you notice, okay? They're both underlined in that pink color, sort of pink. And then, so that part is good. So then to find big F, I partially integrated. These are partial derivatives. What did I say? Did I say integrate? I mean derivative. So the partial derivatives work out to be identical. And I did it on the Wolfram calculator because other calculators can't do partial y. At the most they can do is like partial x or something. And so I did this on the Wolfram calculator without any trouble. And they check out that P2 does equal to Q1. So we can apply the Green's theorem and find the big F by doing partial integration of dy so F equals to partially integrate, what is that? This is Q, okay? Partially integrate Q with respect to y will give us big F. And well, the big F in this one that came out is tangent inverse of this thing. It does work, as you can see here. If we take the partial derivative of this thing, it does equal to partial x equal to p and partial y equal to q. It checks out nicely. The problem, however, is that well, this thing checks out very nicely. There's just one minor problem, because the denominator here, where let me see. I can't read it. Yeah, the denominator here is the same thing. You see, when you take the partial of this function right here, the top looks like the 4x, which we have. Where's the origin? Right here. The bottom looks slightly different, but they are the same thing. Okay, because when you subtract it, they're both 0. So this does check out. This is indeed p, where p is way up here. All right. So as you can see, p is this formula is the same as this denominator here is the same as this denominator here. So that part isn't the problem. The problem is that this fx, the tangent inverse of this value, is when we require the x and y to be bigger than 0. So there are values such that this function has a denominator equal to 0 in x bigger than 0 and y bigger than 0. Okay, so then we have to reject this formula, and then this is integrated with respect to dy. And then if we integrate with respect to dx, then for big F, then we get a slightly different formula. And that one works out much better, okay? And this one is represented as with 2y on the bottom. Now this is different from this one, okay? Even though they both work as antiderivative. If you have to plot those two graphs in, they're not unique. This is just an integration. If you do integrate dx, this is for the new thing that I got, which looks similar, but they're not identical. Okay, if you plot their graphs, they don't look the same. And if you but if you check the partial x and partial y, they do end up being the same as p and q. So that's the other by doing partial integration, which the Wolfram calculator is able to do. Okay, it's very clever. And I was able to come up with this function, in which case y is bigger than 0, so we don't have to worry about denominators. And so this is the accepted answer, which is also the answer at the back of the book, that this will be the antiderivative of problem 5. So that's how I got this thing. Okay, and the book hasn't mentioned anything about taking an antiderivative, but when you do the homework, then you are basically forced to think about how we're going to come up with this stuff. So taking the antiderivative with respect to x or y can come up with two slightly different answers, which might both work depending on the domain. Okay, because on a different domain we might prefer this answer instead. But in our particular domain, that where we require x bigger than 0, y bigger than 0, this option will be rejected, whereas this option is accepted. Okay, so that should do that. And next, let's look at problem 6. Problem 6 have let me put this down here. Problem 6, we have to integrate this big long thing around the unit circle. The curve is the same. Exercise 3, which says the unit circle, positive sense, all that is good, except that this integration is a whole lot harder. Okay, before we just substituted x equal to cosine our cosine theta, r is 1, so just cosine theta, y is sine theta, we plug it in and everything comes out neatly. Now this thing, however, the original formula itself has sine and cosine in it. So if you plug sine and cosine in, you're going to be integrating sine of sine, which I have no idea how to do that. Okay, so here we are stuck with a very tough integration problem that I haven't tried it in the Wolfram calculator, but I bet you that thing can't do it either, because that thing can't do everything, unfortunately. So I like that, but then the question is, how does the book do it, right? And it turns out the book is going to use a trick, in which it gives us a hint on how to pull off this trick. What we're going to do is use this some circle that's x squared plus y squared equal to r, where r is less than 1, okay? And then beat around and to get things to come out. So here is how we are going to do this. And the trick is right over here in this diagram that I drew. What happens is we're going to go around the unit circle. Okay, that's the outside circle, which you might be able to see this clearly. The outside circle consists of gamma 1 and gamma 2. Okay, and then there's an inside circle with radius just r, those are put into two parts: the top semicircle and the bottom semicircle, and we'll call them gamma 3 and gamma 4. And then the sides, there's the bunch of horizontal lines, which we'll call gamma 5, 6, 7, and 8. Okay, in other words, we're going to cut this thing into this shape, and this matters. Then what we're going to do is we're going to integrate around the top half of the donut, and then integrate around the bottom half of the donut, and then that will give us a sum in which gamma 5 and 6 will cancel each out, because they're the same thing going in different opposite directions, and so will gamma 7 and 8. And then what that will do is that we will have the whole thing being well, anyway, I'm done talking about the graph. Let's start at the beginning. So if the original problem is right here, I'll identify this part as P and the other part as Q. So then first we need to confirm that P2 is equal to this big long thing, okay, which I did on the calculator. You imagine people doing it by hand. But anyway, which equals to Q1, which is another painful thing, but luckily they're the same, so it's not too terrible if you had to do it by hand, and luckily we don't. So that's the first step, is confirm that the Green's theorem applies. Now that we know that, then, well, it sort of applies, because we are going through the center and the origin where the function is 0. So the Green's theorem does not apply in any region that contains the center. Which is why we're doing this cutting business, okay? We're going to cut it into two chunks, each chunk going through the origin, I mean, each chunk avoids the origin by this circle on the inside with radius r. And so for each chunk, then, the Green's theorem applies because the origin is not contained in the domain. And so we work out some of the details, okay? The top part is add the curves together, where counterclockwise is counted as, I don't know, positive, and the other way is negative, etc. Then work out the top part and the bottom part equal to those gammas. Gammas are always calculated as from in the counterclockwise sense. So any gamma that goes the other way will be called a minus, okay, which is why there are some plus signs and some minus signs or something. Anyway, I hope that this is all correct. But anyway, yeah, work this out yourself, right? The details, but you get my point, okay? This in graph here is well, is where I got all this stuff. So anyway, so remember gamma 5 is the same as negative gamma 6 and so on. So by Green's theorem, the integral of gamma on the top, okay, the top is going to be 0. And so does the bottom. And then if the integral of the whole thing will be added those two things up. And being that the horizontal lines cancel each other out, then we will have only let's see, by Green's theorem, then when you add up these two things equal to 0, then eventually you'll get the integral of gamma 1 is the same as equals to integral on gamma 3. Let's see, right. That's just the top half, by the way. Okay, pay attention what gamma 1, gamma 3 is. That's just the top half, which is fine. And similarly, gamma 4 is going to be the same as integral of gamma 4 is the same as integral of gamma 2. And that is true for any r where where r is between 0 and 1. Okay, and that is that's good to know. So then the next thing we're going to do is doing the actual integration by now we're going to substitute the values of x equal to r cosine theta on gamma 3, that is on the inside circle, where r is some kind of constant that's between 0 and 1. And then we're going to integrate everything on gamma 3. Let me look at this first. Now, in plugging in, as I said before, we are going to have sine of sine, right? And how are we going to calculate such an integration? Well, we're not sure yet, but we're going to write it all out, okay, which consists of 2 lines because the original integral is a big, long thing. So we're going to plug x and y as r cosine theta, r sine theta. But in this integration, remember, r is a constant number. Okay, and it doesn't, it's just a fixed circle. So in the integration for a fixed r, the integration stands. We plug everything in, which takes me 2 lines to write it all out. And then if you look at it more carefully, then in there are the 2 things that are underlined with green lines right here. They cancel, they're identical except for the sign, so they do disappear. So we got rid of 2 of these things, which is a improvement. So the whole thing equals to this, which is still not simple because it still contains cosine of cosine and sine of sine in here. So at this point, we're going to pull the trick that the book says in the hint. That is, we're going to let r go to 0. Okay, so then if we let r go to 0, then that will be cosine of 0, which is 1, and then cosine of 0, which is also 1. So we end up with this very, very beautifully simple integration, which is just pi. All right, and then so after all that big pile of stuff, we suddenly collapsed into just pi, and that's gamma 3. Okay, that's the top small circle here. Now gamma 4 will be the same way and also come up to be pi, and then so remember, we already said that the integral on gamma 1 is the same as gamma 3. So what we need is the integral of gamma over gamma 1 plus gamma 2, right? And then and gamma 1 equals to gamma 3 in integration, and then gamma 2 equals to gamma 4 in integration. So let's add it all up, and then that equals to 2 pi. That is which is the correct answer. Now in here, pay careful attention to the signs. Like there's the plus and minus, and it can get very confusing. And I was, I tried my best to keep the signs straight, but it does work out. Well, for one thing, it is 2 pi is the right answer, so that helps. But anyway, just keep track of all the signs and who equals to what. Then eventually you'll get the right answer, which is for problem 6, and that checks out at the end of the in the book answer as well. So next, let's look at problem 8, which is actually we already did problem 8 inside problem 6. Okay, this case is true in general, where we have by Green's theorem we can just if we have some kind of a donut ring or ring-shaped thing, we can split it in half, and then the integral against around the outside gamma is going to be the same as the integral around the inside curve. Well, as shown by a bunch of plus and minus here, that if I didn't get it wrong, that should work out. So next we have problem 9, where it's going to be used for the rest of the homework too. That is the delta U is defined as U11 plus U22, and which is given as 0. Okay, in this case, then we can find something called the conjugate, which is which we can obtain the conjugate by integrating either ux dy or uy dx or something like that. And then anyway, because then everything will work out. Because if v is defined as integral of ux dy, then v2 is going to be equal to ux, and that's by the fundamental theorem of calculus. Well, anyway, so then if we continue calculating that, then v21 is going to be equal to uxx, which is given because we're given that delta u equal to 0. Uxx then equals to negative uyy, and so then the integral of vxy is going to be equal to integral of negative uyy. Well, the reason I write down the xy instead of 1, 2 is just to, I feel like it keeps things a little bit clearer in my head, but you don't need to do that. Okay, you can just write down the 1, 2, keep doing the 1, 2 instead. Maybe it doesn't make any difference. I don't know. But anyway, so the integral of being that this one equals this one, and vxy, which is v21 or v12, is going to be equal to the integral of negative uyy, and which becomes integrating both sides, we get vx equal to negative uy, or I put it another way, what we were looking for is u2 equal to negative v1. So that is problem 9. So problem 10, we are going to base on problem 9. Okay, we're going to find a bunch of conjugates. Well, the conjugates are found, assuming this relationship holds, then the conjugates are found simply by integral of ux dy or uy dx, something like that. So then we are going to apply that for the first equation and formula function. I have I checked the uxx and uyy. It does that is the triangle does equal to 0. Okay, that is uxx and uyy add up, that's equal to 0. And then I integrate the v, the conjugate, then will be ux, where's ux dy, which equals to this thing, and that does check out. And then the part B, I don't think I even bothered to confirm the delta u equal to 0. I just went ahead and calculated what ux is, and then did the v is equal to integral of ux dy, okay, and integrate that partially with respect to y only, then we get this thing. And then C is the same way. We just plug it in and it came out. And then these answers these answers check out with the back of the book. So that's problem 10. So next, let's look at problem 12. We are going to define a conjugate functions in polar coordinates where they're defined such that RU1 equals to V2 and U2 equals to negative RV1. Now, how do we define this thing to have the conjugate? Let's see. Okay, so then the conjugate is, this is problem 12. We will, given these two conditions, okay, RU1 equal to V2, U2 equals negative RV1, we can figure out what V is simply by doing the integration of one of them. Okay, so then based on this first formula, then V2 will be integral of RU1 d theta. That will be one definition of V. We'll just integrate. However, what condition do we need? We still need this condition right here, where for everything that we have said so far to make sense. That is, delta U had better be 0. Okay, and then for that to happen, then we have let's see, problem 12 right here. For delta U to be 0, then we'll calculate V21, which is this thing, and then V12, which is going to be this thing right here. Okay, and what that is, and these two had better be equal. And for these two to be equal, then and let's see, yeah, and U22 equals to this one. And so for these two values to be equal, then we have to have U22 equals to negative of negative RU1 minus R squared U. What is that? U11. So please just stare at this thing for a few moments, okay? And it all makes sense to you. Where V2 is already equal to RU1, so that's how I got the V12 over here. And then, V21 over here, and then V12 is from this equation. Okay, and then this thing comes out. So next, let's look at example problem 13, where we just calculate what we just did in problem 12, and so we calculate that. So U equals a log, and as remember in this book, log means natural log. So then we calculate U1. And then U11, U2, and U22, and plug it into this thing we had earlier, and then this does check out. So this formula works. So even though we don't have answers to these couple of problems, we still know that we're probably on the right track. I just noticed that I didn't finish problem 14. Problem 14 comes in 2 parts. So I'll go do that and finish this section in the next video.